Welcome to Easy-Matter Circuit. In this video, we'll be looking at series and parallel circuits, the basics of series and parallel circuits. So, what do we mean by a series and parallel connection, and how do we recognize a series and parallel connection? A series connection is a kind of connection in which the components are connected together in such a way that there is only one path for current flow. While a parallel connection is a type of connection, or a parallel circuit is a type of circuit in which there are multiple paths for current flow. These are the basic defining characteristics of a series and parallel circuits. Let's consider these figures. From these diagrams, which of them is series and which of them is parallel? Given that a series connection is a kind of connection in which there is only one path for current flow, if we have voltage source across all of these connected loads, this is our voltage source, this is the positive and the negative. We have another voltage source here, positive and negative. Let's have another voltage source in this one. So this is positive and this is negative. And let's have another one here. This is positive, this is negative. The positive terminal of your DC source is always the longest side. And conventionally, current flow from the positive terminal of a source, of a voltage source, to the negative terminal. We have current flow in this direction, and we have current flow in this direction. So in a series circuit, there is always only one path for current flow. So in considering this circuit, look at this. We have only one path. This is the only path in which current can flow in this circuit. So this circuit can safely be concluded to be a series circuit. Look at this kind of circuit. If we have a current flowing out of this voltage source, one current can flow into this branch, another current can flow into this branch, another current can flow into this branch. So this kind of circuit is termed a parallel circuit because there are multiple paths for current flow. If you look at this also, there is only one path for current flow in this circuit. So this is also an example of a series circuit. Looking at this also, this is one branch through which current can flow, another branch through which current can flow, and another branch through which current can flow. So this circuit is a parallel circuit. No matter the layout of your circuit, you just have to look out for the established path for current flow in that circuit. If you have just only one path for a current flow from the voltage source through the loads, that means that circuit is a series circuit. If you have multiple paths through which current can flow through the load, then that means that circuit is a parallel circuit, no matter the layout of your circuit. Now let us consider a series circuit. Given a circuit in this form, if we name this R1 as the first resistor, this is R2 and this is R3. In this circuit, we have three resistors connected across a voltage source. Since there is a closed path, therefore a current flow will definitely be established. Given our currents to be high, from our Ohm's law, we have voltage to be equal to the product of current and resistance. For the voltage source can be denoted as the product of the current and the total resistance. This total resistance can also be called the effective resistance of the circuit. So, in a series circuit, the same current flow through the circuit, but there are different voltage drops across each of the loads because each of the resistors have different resistance. Even though the current flowing through them are the same, the voltage that is dropped across each of the resistors are different. So, across resistor 1, we have a voltage drop of V1. Across resistor 2, we have a voltage drop of V2. And across resistor 3, we have another voltage drop of V3. So, the sum of all the voltage drops in a circuit is equal to the supply voltage. Now, given that the supply voltage is equal to the sum of all the voltage drops in a circuit, we have voltage to be the product of current and resistance. For the supply voltage, it is the product of the current and the total resistance of the circuit. But for voltage drop 1, that is the voltage that is dropped across the first resistor, is a product of the current and the first resistance. For voltage drop 2, it is a product of the current and the second resistance, while for voltage drop 3 is also the product of the current and the third resistance. Dividing through by the current, since we have the same magnitude of current flowing through all of them, if we divide through by the current, divide this side by the current, divide this side by the current also. This is going to take out this, and this is going to take out each of the currents. So that means the total current of this, the total resistance of the circuit is equal to the first resistance plus the second resistance plus the third resistance. In that wise, the effective resistance of a series circuit, or the total resistance of a series circuit, is equal to the sum of all the resistances that are present in that circuit. To get the effective resistance of a series circuit, we find the sum of all the resistors that are present in that circuit. Given that the current flowing through a series circuit is the same because there is only one established path for current flow. So the current flowing through a series circuit is the same, while the voltage dropped across each of the resistors are different because the resistance of each of the loads are different, and therefore the voltage that is dropped across each load is proportional to the resistance of each load. Given a parallel connected circuit in this form, if we have a parallel connected circuit in this form, if we denote this with R1, we denote this with R2, denote this with R3. If all of them are connected across a voltage source. In a parallel circuit, since all the loads are connected between two electrically common points, like the polarity of this terminal is common to all of them, while the polarity of this terminal is also common to all of them. So since they are all connected within two electrically common points, that means the voltage that is applied across all the resistors are the same, which is equal to the voltage source. And since there are multiple paths established for current flow, the total current that is flowing out of the voltage source, let's denote the total current with I, is equal to the addition of individual currents that is flowing through each branch. If we have current I1 flowing through the first branch, current I2 flowing through the second branch, and current I3 flowing through the third branch, the voltage that is applied across all the loads, they are the same, which is equal to the voltage source. So the voltage supply is equal to voltage applied across the first resistor, and is also equal to the voltage applied to second, equal to the voltage applied across the third resistor. But the current that is flowing out of the voltage source is equal to the sum of all the current that is flowing through each branch. From our Ohm's law, we have V to be equal to IR. And in that wise, that means our current is the ratio of our voltage and the resistance. So if we are substituting this into this expression, we have the supply current to be the supply voltage over the total resistance or the effective resistance of the circuit. And the current flowing through the first branch is the same as the supply voltage over the first resistance. We have I2 here, I2. We have I2 here, and I2 is the same as the voltage divided by the resistance in the second branch, and we have our I3 to be equal to the voltage divided by the resistance in the third branch. So far that we have the same voltage in a parallel circuit. So if we divide all through by the voltage, that means we'll be left with 1 over RT, which is the total resistance of the circuit, to be equal to 1 over R1 plus 1 over R2 plus 1 over R3. We can effectively say that our total resistance, which is the same as the effective resistance of the circuit, to be equal to the inverse of the sum of the inverse of the resistance in each branch. In exceptional cases, we can have a combination of series and parallel circuits. So such combination is called series parallel connection, and an example of such circuit is this. We have a series resistance connected with two resistors connected in parallel. If we consider this diagram, if we name this R1, this R2, and this to be R3. If you look at this circuit connection now, R2 is connected in parallel with R3, whereas R1 is connected in series with R2 and R3. So this is a perfect example of a series parallel connection. The summary of the properties of a series circuit, as we can see here. In a series circuit, the same current flows through the circuit because there is only one established path for current flow. As we have in this diagram, we have only one current. The same magnitude of current is flowing through the circuit. And also the effective resistance, which is the total resistance of a series circuit, is equal to the sum of the resistance, all the resistance present in that circuit. The supply voltage of a series circuit is equal to the sum of the voltage drops across each of the resistors. If this is V1, this is V2, and this is V3. So the supply voltage, which is the voltage energizing the circuit, is equal to the sum of all the voltage drops across the circuit. And this should be noted that in a series circuit, if any of the load fails in a series circuit, then that means the circuit will be completely dead, because for the circuit to be complete, all of the components in the circuit should be present, and therefore if any of the components burn out, that is going to create an open circuit, and that is going to turn off our circuit. So for a series circuit, all the components must be active for the circuit to be active. In a parallel circuit, the summary of the properties are shown here. The voltage across all the components in a parallel circuit is equal. That means the voltage across R1 is the same as the voltage across R2, and it's also the same as the voltage across R3. But there is different current flow through each branch of a parallel circuit. Like the current flow through branch 1 is different from the current that is flowing through the second branch, and it's also different from the current that is flowing through the third branch. But the total current that is flowing out of the voltage source, which is our I, is equal to the individual currents flowing through each branches. So we have I to be equal to I1 plus I2 plus I3. But the voltage is the same across all the branches. The voltage is the same across all the branches. The effective resistance of a parallel circuit is the inverse of the sum of the inverse of individual resistances. But in a parallel circuit, if any of the components fails, it doesn't affect the operation of other components of the circuit, because each of them are connected directly to the voltage source. In this video, we have been able to go through a detailed basics of series and parallel connected circuits. Don't forget to like this video and drop your review in the comment section below. Click on the subscribe button to see more of my videos as they have been uploaded. I'll see you in the next video.